Let's start with the call. Good morning, good afternoon, everyone, and welcome to the first of the Fire and Gas Detection Technologies webinars, Beginner's Guide to Flame Detection, presented by Dr. Eliot Sizeland. My name is Ian Evans, and I'll be your host for today's webinar. The webinar is being recorded now and will be available later should you wish to review anything that you may have missed. For those that don't know Eliot, Dr. Sizeland, he's a graduate of Swansea University in Wales and received his doctorate from the University of Southampton for PhD work on semiconductor gas sensors. Eliot is also a chartered engineer and member of the UK Institute of Measurement and Control. For this presentation, I would also say that Eliot is one of the foremost experts in flame detection principles and technologies, with over 25 years of experience in the flame and gas detection industry. For the duration of the presentation, your microphones will be muted, but please do use the Q&A function, or I think chat is there as well, to raise any questions that you have during the presentation. We may answer some of the questions during the presentation, but there will certainly be a Q&A session at the end. So without further ado, I'll hand control over to Eliot. All yours, Eliot.
Good morning, good afternoon, and good evening, everybody. Thank you very much for taking the time out of your day to attend this webinar. It is our first webinar, as Ian said, and I have to say it was extremely oversubscribed. We have been quite shocked by the number of people that have signed up. This particular session is entitled A Beginner's Guide to Flame Detection. And I have to say, having seen the registrants, I don't think all of you are actually unfamiliar with flame detection. So there may be a few things in here that are new to you, but hopefully this will be the first of a number of courses. This is the beginner's one. We'll do an intermediate and an advanced course. And at the end of the presentation itself, we will review some of the possibilities for future presentations. I also noticed one of the people that registered for the webinar itself was actually on the initial training course that I did on flame detection 25 years ago. So I thought that was particularly interesting. That person will remain nameless. So in this webinar itself, what we will be doing is talking essentially to begin with about fire. We will look at the ways and means that fire can actually start, the type of what is actually fire in itself. We will walk through some of its qualities, because fire actually is incredibly important to us as a society, but of course it has some significant drawbacks, and those drawbacks means that we need a mechanism in order to detect the presences of fire at an early stage, which is why we have fire detection. And with regards to that, we will move on. We will ask some questions and look at the principles behind conventional fire detection, which is basically smoke and heat detection, and then move on to the slightly more exotic world of optical flame detection, asking the questions, you know, what is a flame detector? Quite often I get asked questions about technologies that seem similar to flame detection, but actually they're not. They're more like distant cousins. We will then also have a look at what affects flame detection performance, and then specifically focus in on the technology's its strengths and limitations, because it's that primarily allows us to help decide which flame detection technology we will actually look at. Following on from that, we will ask the fundamental question, is there a perfect flame detector? And then we'll also just have a quick review of some of the questions. After this session, a questionnaire will go out, which will talk, it'll give you a bit of a survey about the content of the material. You know, this is a beginner's guide. We will then also ask what you'd like to see in future webinars, and so we shall try and tailor them not only to the content of what you want, but actually in a better way, more closely aligned with the time zones that you're all actually working in. So without further ado, moving mainly into the presentation itself, it's very interesting that I completely updated this presentation itself. And when looking into fire itself, the first thing that occurred to me, well, what actually is fire? And fire is basically a chemical reaction that is called combustion. It also, for us as individuals, it is a sensory perception of actually that process of combustion. And so what we can do is we can see a fire if it's a visible fire. We can smell the fire, the burning materials, and we can feel the heat that would actually radiate from the fire. So it's very much a sensory thing. And one of the things that I had always been taught growing up was there was always a fire triangle. That fire triangle basically were the elements that, if they were all present, allowed you to have combustion. If you took any one of those processes away, the fire would actually go out. Those three elements as part of the triangle were basically heat, or a source of ignition, oxygen, giving you the ability to oxygenate the actual fuel itself, and then you need the fuel, so the actual material that's going to combust. But actually today, people no longer talk specifically about the fire triangle. It's actually called a fire tetrahedron. And there's an additional element, which is pretty much like a feedback loop. That is that there is that chemical reaction which creates the chain reaction that makes the fire continue to burn. If we still take away one of the other elements, for example, the fuel, the heat, or the oxygen, the fire will go out. That's how we extinguish fires. But it's that chain reaction that means that the fire will continue. And of course, fire has been very much a force for good for us. You know, it brings us heat and light, and it has allowed us to develop as humans by developing tools to generate power, for example, and for us to develop overall into a very sophisticated race. But at the same time, fire can be a very destructive force. This is just a very simple example of a fire that occurred just last week within continental Europe. It actually was on a waste recycling facility, and to many people, a waste recycling facility may seem insignificant. But what is one person's rubbish is effectively another person's treasure. And so if we understand what we can actually generate in the way of revenue from a recycling facility, we have the materials themselves that can be reused. Those materials that can't be reused can be taken away and used in a waste to energy type facility. So today we are putting we're putting less and less product into landfill sites, and actually we are generating more money from rubbish than at any part in the future. So that's one commercial side of this sort of fire. The other part is you can see this acrid, thick smoke that's coming from the fire. And if you have people that are living in close proximity to the fire itself, they could be put at personal risk due to toxic fumes and smoke inhalation. So there's a commercial element, and then there's also the health aspect that needs to be understood. And so the most important thing is, how do we stop a fire getting out of control? How do we provide something that detects fire at an early stage? And there in itself, I've used the word detect. So by understanding the growth phase of a fire itself, we can apply different types of fire detection technology. If we're looking at a very, very early stage, perhaps in a clean type environment like a data center, then we might use the aspirated type smoke detection system that would be linked directly into the control cabinet of each of those data packs themselves. Then there are different types of optical and ionization smoke detection. And also today we have multi-criteria type detectors that combine different types of optical technique with perhaps even carbon monoxide detection, and also with regards to heat detection. A lot of that has actually been done to improve false alarm immunity, but some of it's also been done to try to help to detect the fires more easily. These types of products, the smokes and the heat detection, effectively what we would know today as conventional fire detectors. And somewhere in the middle of the growth phase of the fire, when we have a physical flame at a very early stage, we will use optical flame detection. And so in the next couple of slides, we will talk about these approaches. So with regards to conventional fire detection, this in many ways is the default position. In fact, most of the standards around the world are quite prescriptive for the use of different types of heat or smoke detection and the area of coverage that you would actually get from these types of products. But in general, these detectors are actually only used indoors. They tend to only be ceiling mounted, and that can mean that they're not so suitable for very high structures, because what you have with a fire is the smoke particulates or the heat have to transfer or travel all the way to the detector itself. So you actually have quite a long transit time. One of the issues you also have with very large structures, particularly in the summer, is you will have the sun heat the top of the building itself, which can create a thermal layer, which can actually make it very difficult for those smoke particulates to actually punch through to where the detectors actually may use. So in the example that we're sort of seeing here in the image on the right, they're actually using what is quite a large fire itself in order to punch enough smoke to the roof of the atrium there for the smoke detectors to actually work. Whereas if we had had perhaps flame detection in the lower atrium area, we might have been responding to a fire within a second or two. But of course, I'm not necessarily saying that flame detection is the most suitable product for this application, because we have to balance the risk with the cost. Now, when we're looking at flame detection itself, we have to understand what is the expectation of a flame detector. Well, first of all, it must always detect a fire, and therefore it must not miss fires. They typically are used in very high value applications, and so the integrity of the unit and the ability for the device to perform when needed is absolutely critical. Therefore, a detector must be able to warn if it is no longer able to perform its function. So effectively, it's fail-safe and self-monitoring. The detectors also need to be able to use anywhere in the world, both indoors and out, from the hottest conditions on the planet to the very, very coldest. And while we sort of just pause there for a moment, one of the other things that we need to consider is the type of fire that a flame detector needs to respond to. Some can be particularly large, in the case, for example, of tank farms. Some can be slow and evolving type fires, perhaps fires that may be present on a waste recycling facility. We can also be looking at very fast type of detection, perhaps for explosion type monitoring, and fast fires perhaps for a high pressure vessel that has lost its integrity, and you get ignition. You'll get a fireball type of effect there. So we can have different types of fire scenario, and we need to ensure that the flame detectors are able to respond. Now, what is a flame detector? I've created a very, very simple description for a flame detector. And that is very simply that it's a safety device that uses optical techniques to monitor for areas where a fire should not normally be present. And more than just that, the fire itself should not be a controlled fire. So we are really looking for what I would consider to be hazardous fires. The units have to be fast acting because we're trying to minimize the damage to a facility, because we are looking, in the case of petrochemical plants, massive escalation and potential loss of earnings from the products that are being produced on those facilities. or if we were looking at aircraft carriers, there are some aircraft, particularly with the American Air Force, that actually cost $1 billion each. So you can understand putting in flame detection for very fast acting reasons is an extremely good idea. As mentioned earlier, they need to be able to work in the most extreme of conditions, indoors or out, and have that fail-safe monitoring capability. What a flame detector can't do, however, is actually monitor for a smoldering fire or an ember. That actually works to the realm of the ember or the spark type detector. So that is not a flame detector itself. We do require line of sight, and probably the biggest argument that people will ever say to me is that the products are expensive. Well, you pay for what you get, basically. The other thing that's quite interesting is, unlike smoke and heat detection, there is very little in the way of prescription within standards for the implementation of optical flame detectors. It usually comes down to good engineering practice based on a unique application, perhaps petrochemical plant. So it's a real engineering expertise and design that's needed. Flame detectors, in understanding what they are, it's very important that we understand also what they're not. So if we have a fire that is a controlled fire, for example, a flare stack, then actually the designers of a flame detector have not designed it to actually monitor for that type of fire that should be present and then will go out. It's very, very similar, but they're different. They're not brothers, they're much more like distant cousins. The other type of product that we can be often asked about is actually a flame scanner. That is for a burner application management, perhaps where you're looking for a fire burning within a fire. So for example, on a coal-fired power station, you might use a gas fire to actually ignite the coal, and you're looking using the flame scanner itself to see when the coal has actually ignited, and then you can switch off the gas pilot light. So how does a flame detector work? Well, a flame will propagate or emit energy over a wide spectrum. Typically today, what we will look at with products ranges from the ultraviolet end all the way through to the infrared end of the electromagnetic spectrum. And what we can see is that all fires actually burn slightly differently. And as a result, we will need to employ different characteristics of the detectors based on the optical design in order to tailor the product to the actual fire that's going to burn. And on that exact same theme, not all fires are the same. Here we have a heat shimmer. Well, that is actually a hydrogen flame that is burning. And here you can see the gentleman will come along and just use a brush to prove that there was a burning flame. So we can see with our own eyes that the hydrogen fire itself during daylight is virtually invisible to the naked eye. It's just like the heat shimmer that you can see on a very, very hot day. And it's only when you bring something into contact does the fire suddenly become visible. In fact, it's not the hydrogen that's burning, it's actually the broom itself. And it's important that we understand that technology drives the detection mechanism itself. So what actually affects detector response? Here we have quite a broad list. We've already touched on the fuel that we will look for. We will then look at the detection distance of the fire from the source. We can also look at the size of the fire. We can think about detector sensitivities. We will look at the detection technologies, the false alarm sources and the inhibitors, and then the environment, how that can have an impact on the detector as well. Finally, there's the field of view, and the field of view, some manufacturers will stretch the field of view and others actually do their level best to control it. And in subsequent webinars, we'll delve into some of these areas in a lot more detail. In this particular presentation, we're really going to focus on the principles of the detection technology itself, understanding the strengths and limitations from the false alarm sources that we've got, and also understanding some of the environmental impacts that we actually are looking at. So The very first type of flame detection technology that was utilized was a UV detector. A UV detector is basically a Geiger-Müller tube. So it will sit monitoring an area and it will receive photons, light energy. The more photons per second that are actually hitting the sensor itself, the greater the likelihood of a fire being present and therefore raising an alarm. Because of this, it's a straightforward count of light energy. We can set a straightforward threshold, which means the detection technology itself is actually very, very straightforward and very fast. And as a result, UV flame detectors have historically been used for many years for munitions type manufacturing because they were so fast. Typically, you would get a response in less than about 25 milliseconds. The beauty of a UV detector is that actually it can detect virtually all types of fire because a fire is emitting light energy, whether it be visible or visible. But the technology does have some significant limitations. The main limitations with the product actually arise from false alarms, particularly from hot work. The main areas would be things from like grinding, arc welding, and sparks and electrical arcs would also create false alarms. In the past, and in fact even today, lightning strikes can actually cause UV flame detectors to false alarm, which is why we would typically utilize them with a time delay. There is one significant other drawback. So because optical contamination like films of oil or dust or sand can actually blind the detectors, what we also found was that people would put plastic bags over the optics themselves. The very nature of putting a plastic bag, which is effectively a hydrocarbon, over a window itself, the unit will tell you it's working, but unfortunately that UV energy will not pass through the bag. So again, they're not going to work. In the past, UV flame detection was pretty much the only option that people had for hydrogen flame detection. And as we move forward with energy transitions to a cleaner world and the move to hydrogen and ammonia as different types of fuels that are being utilized, people will move away from UV in favor of other types of detection technology. So UV was the first type of detection technology. Then we moved on to single frequency infrared. Now, single frequency infrared is actually slightly slower than a UV-based detector because the mechanisms for detection are different. So here we would utilize a pyroelectric sensor hidden behind a filter. The filter that's selected will determine the characteristic fire that would normally be detected. In many instances, we would utilize a filter centered around approximately 4.4, 4.5 microns. That will allow hydrocarbon fires to actually be detected. Now, in itself, that isn't sufficient for detection because infrared is heat. And what we need to make sure is that we are detecting a fire and not just a hot radiating black object, for example, or hot object. With regards to the black body radiation, if it is just there and it is static, it has no movement, whereas a fire actually moves. Typically, a fire will flicker between about 1 and 10 hertz. And so a single frequency infrared flame detector will always utilize a particular filter frequency. It will have a flicker frequency associated with the movement of the fire itself, and it will have a set energy that we're actually looking for. The great strengths of the infrared flame detector is that it does not really respond to the hot work process that the UV detector was responding to, but water and icing on the optics actually can stop the detectors from working, and the earliest types of detectors did not have heated optics. In some parts of the world, what they actually then went to do to improve false alarm immunity was to combine a UV and an infrared detector into the same unit. Here, the great benefit was that you actually had virtually no false alarms for these two detection technologies that would coexist, which means that having a false alarm itself was extremely difficult. But the challenge with those technologies is that anything that would affect the UV channel and stop it working, or anything that would stop the infrared channel and stop that working, would mean that the detector may not actually be may not perform when it was needed to. Today, UVIR detectors are one of the two main technologies that are actually being utilized. The main technology that is actually taking over even from UVIR based flame detectors is actually the IIIR or the multi-spectrum type flame detector. And multi-spectrum IR flame detector leans very, very heavily on the single frequency IR. So we are utilizing very much the same sort of wavelengths that we would have utilized for the single frequency IR, but we are now employing additional sensors, additional wavelengths to provide more information, typically about how to manage false alarm sources within the field of view. The great benefit about the multi-spectrum IR flame detector is that now we are able to detect fires at further distances, and we have a much higher immunity to false alarm. Almost all IIIR flame detectors nowadays have heated optics, and so icing and water actually on the optics themselves has really gone away as one of the problems associated with infrared flame detection. Now, the wavelengths that are actually used with the multi-spectrum detectors actually specifically define the characteristic fire that the unit is going to respond to. So if we're working around the 4.4, 4.5 micron region, we know we are looking at the hot CO2, which is one of the products of combustion when a hydrocarbon fire is actually going to burn. Here we can see the chemical formula, and so what we're doing is we are utilizing this wavelength for hydrocarbon fires, and one of the benefits is that the Earth's atmosphere actually screens out light coming from the sun at that wavelength, meaning that the detectors employing 4.4, 4.5 microns are practically speaking solar blind. So that's a real advantage with the IIIR flame detection technologies. As a side comment, one might say, well, what if I'm going to have my flame detector looking directly at the exhaust of a gas turbine that is being burnt on a hydrocarbon fire? Well, that gas turbine itself is emitting a lot of hot CO2, and potentially that could cause false alarms depending on the sensitivity and the proximity of the detector to that exhaust. So that's something that is a known quantity. And when we move on to the more advanced webinars, we'll talk about how we can overcome some of those issues themselves. So that would be for a hydrocarbon fire. But nowadays we've moved very much away from from UV-based flame detectors for hydrogen fires, and we need to use a different wavelength. Typically, the manufacturers will work a little bit further back down into the infrared around about 2.7 microns. And here, when we look at the products of combustion, we can see that what we're trying to do is basically to detect water vapor. The IIIR detectors on the market that are being used for hydrogen flame detection will still work at the 2.7 with two guard bands that are looking for those false alarm sources. So what we actually have today are devices that are much more immune to false alarm than UV devices, and also they're more capable of withstanding optical contamination. If we were to have a quick sort of walk through the technology evolution as time has progressed in the last, say, 40 or 50 years, we very much started out looking at the UV-based flame detection technology, but pretty much by the end of the 1990s, all of that has gone away, and people have moved on to UVIR or single frequency IR, and then some people have started to add additional sensors. If we bring things right forward to today, pretty much the world has fallen into two camps nowadays. We are either looking at triple IR flame detection, very much for outdoor use and for special fuels that we will be looking for, or we would be looking at UV IR based flame detection, and typically they're used for more exotic fires, and also typically they're more used indoors. And also on the market nowadays, there seem to be a number of sort of fire and security type companies that are focusing more on video analytics, particularly looking at things like smoke detection and also reflected fire detection, mainly for indoor use. So we've moved through the technology part of the presentation and we're coming right towards the end, and we have to ask the fundamental question: is there a perfect flame detector? And today there simply is not. We still have to match the needs of the application, understanding whatever sources of false alarm might be present, the desensitizing factors that may be present, understanding the speed of response that's needed, and then on top of everything, we have to understand what is the risk, or what is it we're trying to protect, because false alarms are very, very expensive, and it's important that we're able to ensure we capture the fire and not have false alarms, and that always has to be driven by a cost. So moving on, we've come to the end of the presentation itself. This presentation is entitled a beginner's guide to flame detection. And so what we've basically done is review the flame detection technologies that are commonly used, understand their strengths and limitations. Coupled with that, we get a good feel for the environment in which the detectors are able to operate. I hope that you're able to now recognize that a flame detector is a product that is looking for a fire that should not normally be present. It is not looking for a controlled fire. And right towards the end, we've, I think, firmly answered the question: is there a perfect flame detector? And there clearly isn't, which is why all manufacturers have a broad range of products that match the technology with the fire that you're actually trying to detect itself. And by way of sort of a teaser, if you like, we are going to send out, as I mentioned earlier, a survey that will talk about the different types of webinars that you are interested in. We have a broad range of applications that we apply our technology for. And in addition, there will be at least 1 or 2 additional technical presentations, non-commercial like this one, where we talk about the design criteria of what's needed behind applying flame detection technologies. So without further ado, I must thank you very much for everybody turning out. As I said, that the presentation was massively oversubscribed, which is why we had to stop the registrations. We can certainly do smaller, more intimate and focused sessions going forward that can be very much driven by application. So if there are no specific questions, I just say thank you very much and enjoy the rest of your day. Thank you very much.
Thank you, everybody.